When it comes to coordination compounds, just like in organic, so isomers, just like in organic, we have two kinds: structural isomers as well as stereoisomers. When it comes to structural, unlike in organic where we have chain, functional, metamers, or positional, here we would have something called ionization, solvation, ligand, linkage, coordination, and polymerization. These are the different types of structural isomers. Just like in stereoisomers, we have geometrical and optical. Here also we will have geometrical and optical isomers. Okay. The fundamental principle which lies in organic compounds is that there should not be any change in the molar mass. Here also it's the same. One important aspect in coordination compounds is you should not be changing the structure of the molecule if you are consider them as uh, isomers, which means the secondary valency of the complex should remain the same. If it was octahedral, it should remain octahedral. If it is tetrahedral, it should remain tetrahedral. If it is square planar, it should remain square planar. Okay, next. The first thing you will notice is ionization isomers. Here, there is an exchange of uh, ions which are either acting as ligands or present in the ionic sphere. For example, SO4 2 minus and Br minus. When you exchange these two, right, that creates ionization isomerization. Got it? For example, if you notice the coordination number here is still 6. Coordination number here is still 6. But sulfate in this case is acting like a ligand. Here bromine is acting like a ligand. That's a major difference. Okay. So if you have such kind of difference, then we call it as, ionization isomerization. Got it? Another cases, let me give you one more example here. For instance, if you have anything like CR, Cl3, correct? And we have Cl3 and H2O, not 3 here, 2. Cl2, H2O, 4 times. Outside, we have bromine. So this compound, as we interchange chromium and chlorine here like this, one bromine, one bromine inside and one chlorine inside and one chlorine completely outside. So these two would become ionization isomers. Another example, if you notice, if you have Cr, Cl, Cn, NH3 4 times, and we have Br. In this case, you would see if you compare this, this, and this. So once I could exchange cyanide outside because that is also an ionic compound. That is also a ion which has charge. And here I can also exchange chlorine, correct? Once bromine inside, chlorine inside, got it? And I can also make, got it? So you could notice once bromine is outside, once cyanide is outside, one chlorine is outside. Okay, so sorry, that is the three cases which you can create, right? So these three will become ionization isomerizations. Okay. For example, if the compound A is given, this is let's say compound A, compound B, and compound C. In the questions, it will be saying it will be said that A, B, C are isomers of each other, and when it is treated with AgNO3, you are getting a yellow PPT, pale yellow PPT. When you are treating with silver with excess amount of KCN, you are getting a complex. So, which is understood that it might be CN four times, sorry, CM twice with minus. This is that complex. Or if you are simply reacting with AgNO3 and you are getting a complex which is white color, which is clearly an indication that it is the third isomer. Okay, so based on this information, you should be able to predict what is the actual uh, reactant or what is the actual complex. Got it? So this is about ionization isomerization. Got it? Next, the second one. Second one is about hydrate isomerization. Second one is about hydrate isomerization. Hydrate isomerization is to do with how we represent number of water molecules inside and outside. For example, you know that this is how we represent the Warner's representation. For this, this is how we represent the Warner's representation. For example, if this compound is given and it is been asked how many number of hydrate isomers are forming. So what you will do like this, that H2O, first let's say H2O 6 and Cl3. This is one combination I can imagine. Correct. This is one combination where all six water molecules are inside. Next, the second combination is I could also imagine a case where five water molecules are inside. One is inside here, and two chlorides are outside, and one H2O is outside. This is still possible. You know how is it possible? Is that this complex, that is this complex, that is cobalt H2O 5 times and Cl. Coordination number is still 6. It has plus 1. So this plus charge might make a hydrogen bonding with the lone pairs of oxygen, correct? And on the other hand, the hydrogen which is present here will make a hydrogen bonding or attraction with the Cl minus here, right? So this will be delta positive, and here this will be delta negative. This is how we can hold a water molecule outside, which means if a water molecule is outside the complex, it is mostly because of its dipole-dipole attraction or because of the hydrogen bond. Okay. So like that, how many water molecules I can put it? See the next case also. I can keep cobalt H2O 4 times, right? Uh, and two chlorines inside. Sorry, two chlorines inside. Here I should write Cl2. Okay. Two chlorines inside. Here there is one more chloride, minus and delta plus. So now this time there are two water molecules. So that makes it plus here. This is plus 2. So that makes it plus here. And this plus might be again attracted by the lone pairs of water. There are 2 moles of water here. So like this, probably there is one more water molecule which is also getting attracted to it. Like this. Okay. And chlorine is being attracted by both these water molecules. Like that. This is also a possibility. What is the learning out of it, students, is that there should be at least one ion outside which can make a hydrogen bonding or intermolecular dipole-dipole attraction with water molecules. If there is no water, we will not be able to figure out how many water molecules, how many number of hydrate isomers we can. That is, in case if you have cobalt H2O 3 times and Cl3, correct, and outside there are only 3 water molecules. Now making this connection with water molecules becomes zero because this is also uncharged. This is zero charge. So as a overall complex, it does not have any charge. So separating this as a crystal with 3 water molecules becomes difficult. So this isomer is difficult to exist. So we will report this A, B, C, and D. So we can say A, B, C are hydrate isomers. Hydrate isomers. A, B, and C are hydrate isomers. Okay. All good, everybody. This is about hydrate isomers. That is one water molecule, at least one water molecule should be outside, but it must be definitely bonded with some anion outside. Next one, the third type of structural isomer is linkage isomer. Linkage isomer is only observed in the case of ambidentate ligands. That is, a cyanide could attack from either carbon's end or nitrogen's end. SCN minus can attack from these two ends. Nitrogen can attack from, NO2 minus can attack from N end or O end. Here O end or N end. Here also O end or sulfur end like this. Okay. So in that case, what we can say, suppose if we take an example, let me take an example here. So I have cobalt NH3 4 and SCN twice, okay, chlorine. Suppose if this is the compound given, I need to find out two things. First, number of isomers, how many are possible. Second, number of linkage isomers, how many linkage isomers are possible. Okay. First, let me show the linkage isomers, everybody. You know that since these two SCN are connecting, the first isomer would be the one where sulfur and sulfur are only connecting. That is CO, NH3 4 times, SCN and SCN. Okay. And outside there is chlorine. Second isomer will be where only N and N are connecting. So that is CO, NH3 4 times, NCS and NCS. Outside there is chlorine. Third one, we have N and S. So then we will have cobalt, NH3 4 times, NCS and SCN connection to metal. Okay. Fourth one, will there be any fourth one? No, because NS or SN is one and the same. So there are three of them. But listen up. I can say there are three linkage isomers for the given isomer. For the given isomer, there are three linkage isomers. And generally, this is the language of JEE questions also. If this compound is given and you are asked only linkage isomers, then you will write answer as three. 1, 2, 3. Three linkage isomers. But if the question is said that find number of isomers, now I know that this can also show ionization isomer because chlorine can be pushed in, SCN can be pushed out. If we do that, then how many different isomers I can get? Check out. The fourth one being, right, I can have one N connection and one Cl connection. So that makes it cobalt NH3 4 times, SCN1 and Cl1. And outside you have SCN. Now, outside it is ionically bonded, so it does not matter what is the direction, whether it is connecting from sulfur end or nitrogen end, it does not make any difference because it is ionically bonded. Ion means the entire ion has a charge of minus charge, and that minus charge is getting attracted. So it does not matter outside how it is, but inside we should know that it is N connection. So N connection means NCS. The same could be written with S connection also, one chlorine inside, right? So same could be written as with cobalt and SCN connection. SCN connection, correct? So these two are other possibilities. So what is the answer you will report here? Number of possible isomers will be 5, and number of linkage isomers for given complex. For given complex will be how many? For the given complex, we have 3. Okay, 5 and 3. Done. So this is the way you need to check it. I hope all of you understood this logic. Okay. Let me take another example here. Suppose if I given you FeSCN thrice and H2O thrice. So for this particular complex, find number of linkage isomers. In this case, I have to find out number of linkage isomers. So check out the connection first. One is S connection. Second one is N connection. Third one is N connection. Fourth one is S connection. Correct? Only these four are possible. So answer is 4. Another example. If you have potassium ferrous with SCN thrice and NO2 one time and H2O twice. This is how the complex is. So now notice what are all the possibilities here. Find number of linkage isomers. What are all the possibilities, guys? First possibility is we can have S connection, right? S, and yeah, here the connection can go from O end or N end, correct? So here I'll get two isomers. Second, I can have N, and then from NO2 I can have, sorry, first is SSN. We can have N connection also and O connection also. Again, I'll get another two. Third one, I can have N and N, and I can have again N and O connection. So again, one more two. And now lastly, N connection with here it could be either N or O. So another two connections. So total are 8. Answer is 8. Okay. So please everybody check the linkage isomer and let me know if you have any doubt in this case. Everyone please go through. See, the next case is about coordination isomerization. See, coordinate isomerization as in when you have two different centers, central metal atoms. That is, let me show you with an example. If you have CuNH3 4 times and cobalt Cl 4 times, you can take this example. Now, in this case, I can say that the oxidation state for both of them should be same, which means this is Cu NH3 4 times 2 plus and cobalt Cl4 2 minus. This is how the complex actually exists. Now, if I make some combinations where the chlorine is coming on this end, right, and ammonia is going on to this end, so then the coordination of that ligands with the metal changes. How many such possibilities I can have? Check. Cu NH3 3 times 1 Cl here and cobalt 3 times chloride and 1 ammonia here. This is first isomer. Check out the second one. Second one is about when you have Cu NH3 2 times and Cl2 and cobalt NH3 2 times and Cl2. Third isomer, if you notice, we can have Cu NH3 1 time and Cl3. And here we have cobalt NH3 3 times and Cl. And last one, the fourth one, if you notice, so we will get this as Cu Cl4 completely and cobalt NH3 4 times completely. Okay. So how many different isomers we are getting in this case? Correct? 4 of them, right? But wrong. Although combination suggests there are 4 of them, the number of actual isomers are 3 only. Number of coordinate isomers are reported as only 3. Why, check this out. When it comes to when it comes to the first case, sorry, when it's come to the first case here, so including this, sorry, I have to mention that as well, that including this we have total 4, including the above one we have 4. So first case we have here is +2 and -2 as the oxidation state. Second case, now the chlorine has shifted here, so that makes it +1 and -1. Now here it becomes 0 and 0. Now tell me, since this is 0 and this is 0, do you think it will have any affinity? Since it does not have any affinity, this cannot be counted as a complex which is cation and anion. It is neutral. So neutral complexes here, both will act two independent complexes. It is not going to act as one entity. So hence this cannot be considered as an isomer. And now we have -1 here, we have +1 here, and lastly we have -2 here, and here +2. In rest all the cases, they are the complexes have the charges, so they will have attraction. So how many total number of possible coordination isomers is 4. Clear? Now, what will be the scenario if you have 6 ligands? That is chromium NH3 6, sorry, this, and we have cobalt Cl6. This is the one which you have. So now what would happen here? So let us see how many different cases we can get. First case is when you have oxidation state as +3 here and -3 here. This is first scenario. Second scenario is when you have chromium NH3 5 and Cl here, and we have cobalt Cl5 and NH3 here. These are second scenario. Then if you notice chromium with NH3 4 times and Cl2 inside, cobalt 4 inside and NH3 twice here. So this is the other scenario. Next, chromium NH3 again 2 times Cl4 here, and cobalt NH3 4 times and Cl2 here. And lastly, chromium NH3 1 and Cl5 here, and cobalt NH3 5 and Cl here. Last one will be chromium all Cl6 here, and cobalt NH3 6 here. If you remember, the 3-3 wala case will not come. 3 ammonia, 3 chlorine, 3 ammonia, 3 chlorine, because the same problem arises. Both will have 0 charge on them. So therefore, here this will be +2, +2, -2. Second one. Here it will be +1, -1. Third one. Here it is reversed. -1, +1. So this is fourth one. Here it is -2, +2. So this is fifth one. -3, +3. This is sixth one. So how many total isomers? Total isomers are 6. Okay. I hope that you guys understood how to do these cases. Any doubt here? Okay. Done. Next one is about polymerization isomers. Check out polymerization isomers here. First one. Polymerization isomers include copper, ammonia 4 here, and cobalt Cl4 here. Okay. So here you can clearly notice that this is +2 here and -2 here. Okay. Sorry. Polymerization, right? So in the case of polymerization, so it is like this. If you have n complexes, then you are expecting to get one particular complex like this. All right. For example, if I take 2 moles of platinum Cl2 NH3 twice, and this got converted into, you know, PtCl4 and Pt ammonia 4. So I can say that, hey, this is, I took 2 moles first, but now it has become 1 mole of complex. Molar mass is same. So then we call it as a polymerization isomers. Now, is it the only possibility? No. If you take this is 1, the second possibility is when you have PtCl3 and 1 ammonia, and on the other side, we will have PtCl1 and 3 ammonia. In the first case, the oxidation state is +2 here and -2 here. Here it is +1 here and -1 here. Now I won't be able to write the 0 and 0, 1, that will not exist. And even if I reverse this, so since the central atom is the same, the other form will also be same. That means if I push chlorine here, 3 chlorines here and bring 1 chlorine here, that will be still the same compound only because the central atom is the same. So how many isomers you will report in this case? Total 2 isomers. What are the types of isomers here? 2 polymerization isomers. Okay. Suppose in case I take 2 moles of CuCl6, okay, CuCl6, sorry, Cl3, CuCl3, not Cu, cobalt, chromium. See, chromium Cl3, and I have H2O thrice, 3. If these 2 moles have been taken here, then how many number of dimer polymerizations you can get? That means you can get only 2 from 2 moles, how many different polymers I can get? Check. The first case being we have Cr all 6 Cl3 on one case, Cr all water molecules on the other complex. This is the first scenario. Okay. Sorry. So then Cr, then we have Cl5 and one H2O here. Then we have Cr, then we have H2O 5 times and one Cl here. Thereafter, I can get Cr, Cl4 and H2O twice, while here I can have Cr, H2O 4 times Cl2. Okay, rest all will be again repeated because if I put this as Cr3, H2O thrice, that is not going to exist because it will get 0, 0 charge. And any other combination is a repeat of this one. So here it is. You can see the charges +3, -3, +2, -2, +1, -1. So total isomers are 3. Done. So I guess the polymerization isomers is clear, everybody. Okay. So you would be asked like this, Vita, if I take 2 moles of this complex, find out how many number of polymer isomers we can get. Got it? Okay. Next, what is the other isomers we have here? Coordinate, ligand. Right. Next one is ligand isomer. Got it? So in the case of ligand isomer, it is about the isomerization within the ligand. Sixth one is about ligand isomerization. Okay. So when it comes to ligand isomerization, please check this out. For instance, if you have, let's say, nickel is present here. Nickel, I have, En Got it? I have En twice here like this. Got it? Ethylene diamine. Got it. So I can also write it as nickel ethylene dimethyl. No, Tn, not En. I'll take these two. Nickel Tn twice here and Pn twice here with 2 plus and 2 plus. What does that mean? See, in case if you have nickel, I have two connections of Tn and Tn. What is Tn, beta? Tn is trimethyl trimethyl propane propanamine. Okay, trimethyl propanamine. So that is N connection with three carbons like this. And here also we will have N connection and N connection with three carbons like this. Okay. So overall charge is +2 on this one. Next one, when it comes to Pn when it comes to that means it is about propane 1,2-diamine. So Pn is 1,2-diamine and propane. So we will have like this. We will have N and N connection. Here also we have N and N connection. But here number of carbons are only 2. The other carbon is only there as CH3. Now, like this we will have, and another carbon is CH3. So this is Pn. Okay. So you can see the change is happening only on the ligand's end. Ligand's molar mass is same, but one is with NH2, NH2 and 1,3 position. In the other case, it is NH2, NH2 and 1,2 position. This is called ligand isomerization. All good? Okay. So everybody, these are structural isomers. Got it? Now let us do stereoisomers. So when it comes to stereoisomers, we can either have a 6 ligand system or a 4 ligand system. Okay. What do you mean by that? That is, I can either have 6 ligands, and within those 6 ligands, which secondary valency being 6, what are all the possible geometrical or stereoisomers we will have? That is one thing we need to check. Or either you should check in terms of how many number of optical isomers we can get. Got it? How many optical isomers we can get. So these are two things we need to observe. Got it? Right. So let's see. Let me start with one simple question. Cases here first. Let me start with coordination number 4, which is easier to understand. When you have coordination number 4, structurally there are only two possibilities. Structurally, one is square planar, square planar. Square planar, we will have hybridization as dsp2, and generally it will not have GIs. Okay, clear? This will have, it will have GIs, maybe. Optical isomers, generally not. So optical isomers are not observed because most of the time you will have plane of symmetry. Only in few cases where there is no plane of symmetry, that's when you might still have square planar, and yet you might have optical isomers, but otherwise we'll only have geometrical isomers. Okay, clear? So this is one thing you should need, you need to understand that, like what will be the isomerization cases here. Got it? Next. If you have optical isomers, what do we search for? We search for, there should be no plane of symmetry, there should be no center of symmetry. In fact, there should be no alternative axis of symmetry. But alternative axis of symmetry are hardly the cases observed in the case of complexes. Next one is about geometrical isomers. When it comes to geometrical isomers, mainly you need to see the distance between the species. That is, the distance between A and C is varying in some other isomers. That means they are geometrical isomers. So if AB, BD, AC, BC, all of them are at a similar distance, then we say there are no geometrical isomers existing here. So usually in tetrahedral geometry, we do not find any geometrical isomers. In any planar complex with POS cannot have optical isomers. Plane of symmetry is there or center of symmetry is there. You will not find any optical isomers either. Okay. So first let's start with the four ligand system here. Ma4. That is M as in metal, A as in ligands. So we have M and then we have A groups here. A, and A. Got it? How many geometrical isomers I will have? No geometrical because I can't find any cis and trans. How many optical isomers? No optical isomers here. Similarly, what if you have M, A, and B? Now think about it. Placing B on any other position, will it generate any different isomerization? So no. So no geometrical isomer. This is square planar. So square planar usually have, planarity itself is a uh, case to avoid optical isomers. Next, Ma2B2. In the case of Ma2B2 means I'll have A and A, B and B here. Now notice one thing carefully. If this A and these two A, you take any reference of two, if those reference atoms are adjacent to each other, we call it as a cis isomer. While if you have A and A here and B and B here, in this case, the same reference atom are away from each other or diagonally aligned, hence they are trans isomers. So only these two possibilities to two GIs, and still there is a planarity, so no optical isomers in this case. Alright, so you will not find any optical isomers in this case. Okay. Right. Next, Ma2BC. In the case of Ma2BC, notice this case here. So in such case, I can say M, we have A2BC here. So I can say A and A are cis to each other and B and C are cis to each other. So that makes it cis isomer. And on the other hand, we can have M. A and A are opposite to each other and B and C are also opposite to each other. Does it make any difference if I write B here and C here? No, structure will still be same. It is superimposable. Therefore, geometrical isomers in this case are 2. Optical isomers still you will not find anything because there is a planarity here. Okay. Next, MABCD. MABCD here. So I'll have 4 such groups here. So let me just copy this one. So check this out here. We can have this as A, B, C, D. I can say that A, B are cis to each other. And here A, B are cis to each other. But D, C are also cis to each other. Now, correct? Why this is important is now earlier D was trans to A. But now A and D are cis to that. And here in this case, A and B are opposite to each other. And C and D are opposite to each other. Now, does it make any difference putting D here and C here? No. Therefore, geometrical isomers in this case are 3. And optical isomers, obviously, still all molecules have planarity. So, no optical isomers. So, this is MABCD cases. We'll have 3 geometrical isomers in which 2 are cis and 1 trans. Okay, 2 cis and 1 trans. Okay, next. Suppose if you have MAA twice, in this case, we can have A and A here, A and A here, and the connection will be bidentate, so it is connected here like this. Now, what I'm trying to tell you guys, suppose, clear? Okay. In case if you have A and A here or A and A here, is this possible to go all the way trans like this and all the way trans like this? Answer is no. This kind of connection is not possible because a ring always has to have some bend at a metal surface. So, but if it is linear, does it make anything like, semicircle kind of cases here like this? No. So that means this isomer existence is not possible. So whenever you have bidentates, right, the restriction is always it has to be on the cis form only. Trans form of a bidentate does not happen to be there. Correct? So that is a scenario we need to understand. Yeah. Just a second. Right. Check this out. So M A A dash. You see we have A dash A A dash, or you can write it as A B also. Okay. You can take any case here. So I can have A dash here and A dash and A. So that means these two connections and these two connections here, that makes it cis kind, and these two connections and these two connections make it trans kind. So geometrical isomers are two. Optical isomers are still not been able to find. Still can't be able to find out this as optical isomers. Okay, everybody clear on this part that when it comes to when it comes to uh, square planar, only these conditions are observed. Now let's see what about tetrahedral cases. In the case tetrahedral cases, we have if all four groups are different, then only we start showing tetrahedral complexes to be optically active. Correct? That is like a chiral center. So nickel having a chiral center like this. We have chlorine, bromine, iodine, and fluorine. In this case, we will have chiral center. So this will become a chiral center. Chiral center. So chiral center will show that optical active. So optically active scenario. Next one. See this case here. This is like a metal having AB twice. It's a bidentate, but two connections are happening for two different elements. Okay. So how would that be? We will have M, and first let me write the tetrahedral skeleton like this. And in this skeleton, we have AB here and BA here. Correct. So if I put that here, so these two connections and these two connections, correct. Now you see that there is no plane of symmetry in any direction. So since there is no plane of symmetry in this case, we can say this and its mirror image both will be optically active. Okay. So that means this one here like this and here. So we have A here, B here, and we have B here and A here. So we have one connection like this and this one. So these two are optically active. 1 and 2, both of these are optically active. Optically active. Got it? Next. Zn OX twice. OX twice is like MAA twice because both connections are from oxygen end only. So if both connections are from oxygen end, then we will have like this. We have M. Okay. Let me show you this one. These two, if I copy here, but imagine we have, there is no B here, everything is A connection. So since this A here and A here, so these two are superimposable. So 1 and 2 are superimposable. Superimposable. Hence, no optical activity or isomers. So no optical isomers are possible for this one. Next is this one. So here connection is both from O, but molecular structure is different here. So for example, we have beryllium connecting with two sides of the oxygen here, oxygen and oxygen, but here connection is from C double bond O, and then it is connected with benzene here like this way. Like this, here also we have connection with O and O, but here we have C double bond O and connected like this. Got it? C double bond O here. And then this is how it is connected. Sorry, one more carbon. Like this, we have benzene here like this. So you can see, now you don't find any plane of symmetry anywhere. So this has non-superimposable mirror, has non-superimposable mirror image, mirror images. Hence, two optical isomers possible. In this case, we'll have two optical isomers possible. Okay. Everybody clear on that? These are the cases you need to know. Okay. So just learn that in which case optical isomers is possible and in which case optical isomers are not possible here. Okay. Notice this is a very interesting case, everybody. We often see that square planar molecules, square planar geometries will not give you optical isomers. But that is something which you are observing that up to this part, there is hardly any uh, geometrical difference. But if the ligand itself have chiral centers, then we might end up having optical isomers also. And that's what you notice in this case, that imagine if this is a case, diethyl here and methyl ethylene amine. So dimethyl ethylene amine in this case. Got it. So this one, this is called butylene amine. Butylene amine. This is butylene amine. In the butylenamine, although it is a planar geometry with respect to central metal atom, notice these four methyl groups. I can say all methyl groups could be up or all methyl groups could be down. That's one and the same. And when all methyl groups are up and down, you'll have a plane of symmetry this way. You might have plane of symmetry this way. So there are two plane of symmetries we can have. So therefore, so when it comes to plane of symmetry, how many we will find in this case? So we will have one plane of symmetry. One will be this way, right? This is one plane of symmetry, and the other one will be like this. So there are two plane of symmetries, one plus one. One methyl up and three methyl down. Okay, clear? Sorry, I meant to say there are two planes of symmetry, correct? So I will count it as only one isomer because it does not have any optical isomers. Now, if at all I have one methyl up and three methyls down, so one methyl is up here and all the methyls are down here like this. Now you will lose out the plane of symmetry, everybody. Now you will not be able to get any plane of symmetry. Since you won't get any plane of symmetry, I'll count it as two isomers. If 1 and 2 here are up and here are down, so still there is a plane of symmetry here. So there is a plane of symmetry, so I'll count it as only 1. Next, if 1 and 3 are up, correct, and 2 and 4 are down like this, these two are down here, correct. So still I'll have a plane of symmetry like this. So that is one more case. Now 1 and 4 are up and 2 and 3 are down here like this. In this case, you will not have either any plane of symmetry this direction, neither you will have plane of symmetry this direction. So you'll have two. So guys, what is the answer you will suggest? So 7. So total stereo isomers possible for this case is 7. Okay, so please check this out. If you have any doubt, you can ask me now. Last two cases are very important, guys. Please check. Right, guys. Now let's look into cases where coordination number is 6. First thing you need to understand one thing. When the coordination number is 6, if AB is here and AC here this way, so you can see ABC this way or ABC this way. These two are one and the same. Similarly, B and B are opposite here, B and B are opposite here. These two are same. So either you write it like this with B and B opposite, or you write like this, B and B. These two are exactly same molecules. B and B here and B and B here are same. I mean, B and B here are same. These two B here and these two positions of B here are same. Okay. So what I'm trying to say is, everybody, please look into this case. Suppose I have a metal and I have, let's say, 6 different positions. These are all different positions. 1, 2, 3, 4, 5, 6. 6 different positions, correct? Now what I'm saying, 1, 2, 1, 3, 1, 5, 1, 6 and 2, 6, 2, 3, 3, 5, 5, 6. All of these are cis positions. Cis positions. They are all cis to each other, adjacent to each other. Or we say adjacent. These are all adjacent to each other. Okay. Next, if you have 1, 4, if you have 2, 5, and you have 3, 6, correct? Then we say these three are transpositions. Transpositions, correct? So these are opposite to each other. Then we say these are opposite to each other. Clear? Right. And second thing, suppose if the atom here and here are same. So this distance and this distance will be same only. Okay. So if we compare the distance wise also, if you notice, correct, distance of 1 2 is same as 1 3 is same as 1 5 is same as 1 6. Okay, these two factors you should understand whenever there is optical isomers. I mean, whenever it is 6 coordination, 6 ligand systems. So when it comes to MA6, Neither we have any optical isomers, right? Let me write down the structure here. So it is like M, we have 6 sides here like this. Copy this part. So we have A, 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 and A. So have you noticed something? This itself is a plane which is dividing the A above and below like a mirror. So therefore, it is a plane of symmetry. Hence, it does not have any optical isomers. Neither you will find anything which is different in terms of geometry. So no geometrical isomers. Okay. Next, if you have MA5B, in this case, we have A, 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 and then B. This is how it is present. Clear? Same logic here also. There is a plane of symmetry. Where is a plane here? You can see these four can become a plane which will divide this A and this A, correct? Like a mirror images. Hence, there are no optical isomers. There are no geometrical isomers. Next, MA4B2. So in case of MA4B2, definitely we can have geometrical isomers here because I can keep B and B opposite to each other, and these four A's are present this way, or B and B adjacent to each other and keep it like this. Now you might wonder, like, sir, what about if I keep B and B here like this? Okay, and rest I put this way. Okay, or might see that, sir, we can keep B and B here and all A here. My point is, guys, all these three are one and the same. These are all same. They're all cis only. Their distance is also same. So therefore, we can have geometrical isomers as 2. Okay. Optical isomers as still 0. Why? See here in the transform, there is a plane of symmetry. You can see this is a plane of symmetry, which is dividing B and B like a mirror. And in this case also, you can notice like this. This will become a plane of symmetry, which is dividing A and A like mirror images. Hence, in this case, MA4B2, you will only have two geometrical isomers and no optical isomers. Correct. MA4B3. In the case of MA4B3, what is the case you would have here? Correct. So check this out. We can write this as A and one side, B, B and B on the other side. Or I can put this as A and A here and B, B and B here. Now listen up. When I put it like this, here we're getting some kind of a plane here between A. You will see here, this is a plane on the octahedron. Correct? Correct. So this is a face of an octahedron. Correct? Because if you notice, this is the octahedron completely. So this will become one of the face of the octahedron. Since it is a face octahedron, we call it as facial isomer. We call it as facial isomer or simply fag isomer. Okay. Next, in case if you have AAA here passing through the center of the metal like this, okay, then this is called meridional isomer. Meridional, or also known as MER. So facial and meridional or geometrical isomers. Now notice if there are any optical isomers. Okay, right. So check it out first. In this case, uh, where do we find it? Please let me copy this and show it properly. Where do we find the plane of symmetry? Okay. So now notice one thing here. If at all I take a plane which is passing through the center here like this. So consider this plane now. So this plane is cutting, sorry, let me rewrite properly. a plane which is passing through the center here like this. This way. So what is it doing? It is cutting through the center. So AA and BB forms like mirror images of each other. Correct? Achha, if you are not able to see it easily in this case, let me rotate and show it. That will be even more easier. Uh, Suppose if I have okay, so if at all I have B and B here, A and A here, A and B here, correct? This is about facial isomers, correct? Now imagine a plane which is passing through the center of this one, okay, like this. This is a plane on which this M, A, B are present on it. So that is definitely dividing, sorry. So we have, where is it? B, A here and B here, like this. अरे क्या करो मैं 1 minute. Pass it through the center. Sorry, I wrote the meridional form. You write down A and A here, B here, and then A here, and another A here. Correct. This is the facial form. Okay, and then we have B here, like this. Right. So in this case, check it out. I'm making a plane which is passing through these three and through this one, that is passing through this plane also. Like this entire plane here. Okay, it is cutting through this. Here is the cut. You're cutting it like this, and this particular plane also have A on it, and here this B on it. So I hope you guys understood how it is going. So this cut. So if you make a cut like this, you can see B and B are becoming a part of that mirror. A and A are also becoming part of that mirror. So hence it has plane of symmetry. Correct. So optically inactive. Optically inactive. Okay. And the other case I have anyways written it. Let me rewrite that case. That is, if you have meridional, that is if you have A here and B here, B here and B here, this way. Got it? So this is meridional. So in the case of meridional, this itself will act like a plane. This itself will act like a plane where it divides A and B. So this is meridional form. So either you write the form in this way, correct, or you write it in this way. Correct. 1 minute. I had to change this too. So here it is A, and here we have B and B. Yeah, now it is the case. This is meridional, guys. Okay, right? So this is facial isomer. This is meridional isomer. So even here we have plane of symmetry. So since there is a plane of symmetry existing, so it is also optically inactive. Optically inactive. So since it is optically inactive, that means there are no optical isomers in this case also. Okay, so geometrical isomers are 2, optical isomers are none. Everybody clear on this case? MA3B3, very important case. Okay, next. Next important case is MA2B2C2. Okay, so what MA2B2C2, everybody. In MA2B2C2, we usually make one algorithm form. That is, whenever you have such cases, MA2B2C2, you always try to put, you know, in the form of groups. That makes it much more easier to analyze. Okay, so check. First, you take this as one group, second group, and third group, and just try to use those groups properly. That is M, sorry, we have M with 6 positions here this way. Now, if at all, let me copy this. Check. What we can do here is, first, I would use like this. A and A is trans, B and B is trans, C and C is trans. So we will designate this as all transform. Next one, A and A is cis, B and B is cis, C and C is cis. So this is all cis form, correct? Next, we have A and A trans, but BB, CC are cis form. So one trans, correct? So second one, B and B as cis, a trans, A and A remains cis, C and C. This is also one trans. Last one, C and C as trans, A and A remains cis, and B remains cis. So this is also one trans. This is the algorithm you got to remember. So primarily, whenever you put M, A2, B2, C2, you will have all trans, all cis, trans, 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 single trans, correct? So if you put this algorithm, I mean, whenever you have multiple number of ligands, then you can always pair them into these groups and then try to look into the cases how many are possible. Clear, everybody? Now, why this makes much more easier, I mean, why this algorithm becomes more easier is, you notice when it is all trans, this is a plane of symmetry which will divide A and A. Similarly, here also there is a plane of symmetry, here also there is a plane of symmetry, here also there is a plane of symmetry. Hence, this one, this one, this one, and this one, they definitely do not show geometrical isomers. And lastly, all cis does not have any plane of symmetry, neither this way, nor this way, nor this way, nor this way. Any way you check out, there is no plane of symmetry. So this is, okay, POS. So if you compare the plane of symmetry, yes, 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 and no. So this is optically active, optical activity here. Optical activity. Okay. No, 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 and yes. Done. So using this phenomena, now we can say number of geometrical isomers are 5. Number of optical isomers are 2. Number of stereoisomers are 6. Because this you have to count it 2 times. One, the given one and its mirror image. So rest of them you'll count it as one time. 1, 2, 3, 4, and then 5 and 6. That will be the number of stereoisomers. Correct? So please check this case very carefully, everybody. It's an important case. MA2B2C2. If you understand this algorithm, you can use this as an application for rest of the cases. Got it? Okay. Now let me show you. Within this, I'll show you more cases now. Check. What are all the other cases we can have? So first case, within this, I can have another case as M A2 B2 CD. If you have M A2 B2 CD, so all you need to do is just copy this part the way it is. Correct? This entire scenario we can copy it. Got it? All you need to do is wherever there is a C and C, you make it as C and D. So I'll just remove this C here, C here, and C here, and replace that with D. So check out D, 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 and D. Okay. Now listen up one thing. Okay. Next, notice one thing. When it comes to all cis here, correct. There is one more added group here. How do we need to show, sir? There is one more group coming into picture. See what you can do. Notice the plane carefully, everybody. A, B, C, D. If on the plane there are two, on the plane, if you have four different groups, correct? You can see on the plane four different groups. Another case where you are getting here uh, A, B, C, D, or A, B, C, D. One second, another one. Where do we have A, B, C, D? A, B, C, D. No. A, B, C, D. No. A, B, C, D. No. A, B, C, D. Yeah, here you can get. See, one, two, three, four. All four are cis two. No, no, this is trans. Yeah, C and B should be correct. See, check it out. If it comes to this scenario, A, B, C, D, since A and B are cis, A and C are cis. But now A and D is becoming trans, right? So that can be changed. So only that part if we change it now. So we'll get this as D and now this becomes C. So this will be the new one because this we didn't had it before. All right. Because as long as AA concerned, BB concerned, CD concerned, they are still cis to each other. But just when you change the C and D scenario, I'm actually getting a new isomer where A and D now are cis. In this case, it was trans to each other, that is opposite to each other. Correct? And you know that this didn't had any plane of symmetry, so obviously this will not have any plane of symmetry either. So now how do we read how many number of geometrical isomers, stereoisomers, and so on? Please check. So number of geometrical isomers in this case would be 6. This time it will become 6, correct? And optical isomers will become 4. And total isomers here, how much you will get? This is 1, 2, 3, 4, 5, 6, 7, and 8. So that makes it 8. So total stereoisomers are 8. Everybody clear? How do we get Ma2, B2, CD? Okay. Next. M, A, B, C, D, E, F. See, how do you write M, A, B, C, D, E, F? See, what we can do. You put M here, easy way out. I'm saying the easy way out is like this, correct? This way. And what you can do, you put 1 as a fixed form and rest of the 5 places you have to arrange them, right? Clear? On the 5 places you have to arrange them. So first check out the geometrical isomers which are possible, correct? So since you have 5 different arrangements here, so 1, 2, 3, 4, 5, 5 different arrangements, what I can do, correct? I mean 5 different locations, sorry. 5 different locations you have here. So what I can do, 5 different locations here, correct? That into, mm, no, what I can do here is 5 into 4 into 3 into 2 into 1. These many arrangements are possible divided by into 2. Suppose if you have C, T, G, F. Okay. So see, it is like 5 factorial here. But in this 5 factorial, what will be the problem that you will get is, suppose I have A and A here. Sorry, A being, sorry, B here. If A and B are trans, correct, then the minute you put B here, B here, B here, or B here, these 4 positions are same only, correct? Isn't it? So suppose A to B here is same, B here is same, B here is same, and B here is same. With respect to A, I'm saying. So that is why, to avoid the duplication, what formula you can use is, always check out how many pockets you have. That means how many positions are free. 5 positions are free. Then multiply that with 3 factorial by 2. That's it. Now that makes it more easier to get it. So how many we can get here? So 5 into 3 into 2 into 1 divided by 2. So how many we can get? 15. So 15 geometrical isomers we will have. 15 geometrical isomers. Got it? If you want, I'll just write it down just for sake of understanding. I'll just write it down, all of them. Sorry, I don't need to copy this part. Copy here. Check. Yeah. So what you can do here is, since you have A, B, C, D, E, A, B, first A, B, C, D, C, D, and E, F. A, B, C, D, E, F. Okay. This is like all cis. Check it out properly. A cis, C, D cis, E, F cis, all cis. Then put the same thing as trans, trans, trans. Correct. So now what I can do here, remove this. AB trans, CD trans, correct? And EF trans, right? This is the one I can do. Now you can see this is like trans. 1, 2, and 3. All of them are trans to each other. Then I told you, like, put it like 1 trans and 2 cis. So do the same thing here now. Okay. So AB trans and put CD and EF like this. So you can see cis and cis, the other one is trans. Similarly, I will keep this as now CD trans, CD trans, CD trans, and AB and EF as still cis. These two. Next one we have EF trans. See, this is EF trans, and then you can put AB and CD. Correct. Those two will remain cis to each other. Correct. Can you see the same fundamental I'm using, same algorithm I'm using? Okay. So if you have it this way, now all you need to do, what keeping this in mind, now change this 4 cases here. That's it. You just have to keep the same identity, all cis. Just change this 4 scenarios here. That is, I can make this as E and F here. Okay. I think it's better to copy the above one. Okay. Now, all I need to do is just change the E and F scenario here. E and F scenario here, because it is still going to be cis only. That's not changing. Correct? And similarly, I can make one more change here. That is B and A here. So B and A here, that is still remains cis. Got it now? So how many different forms I can get? 3. I hope you understood that. So this is also all cis, all cis, all cis. But there are 3 different isomers I'm getting. Geometrical isomers. Now similarly, keep the all trans also the same logic here. So I can keep this and E and F here, E and F here in once, correct? This way, this is the changed part I have done. Okay, here also I'll show the changed part like this. Okay, and the other change which I have done here, other change I can do here is uh, C and D. Once I can change it as C and D. Got it? No, A and B I can change, or C and D. Yeah, C and D. Sorry, C and D also changing will make a lot of difference. C and D here. Now you can see these are not same. Correct. C and D here are remaining trans. Earlier E and C. What has changed here now? Let me check. From first case, EC are cis, these are cis. DF is cis, DF is cis. And FC is cis, FC is cis, EC is cis. No, this has not changed. One second. One thing, another thing I have to change. E and F trans, trans and trans. But this looks same. CD, CD. EF and EF. CD and CD. No change. E and D. This is here, this is here. C and F, this is here, this is here. C and D, C and D. Okay, not change. Sorry. This one is not changing. What I would do, change it from this end here. Okay, because once you have it this form, because between these two, if you notice, F here, if I change these two, um, AB, EF, F and C are still cis and trans like this. Yeah, sorry. In the all trans, I'm not able to change anything. Yeah, let me see this one. This one we can do the change. See what I can do. One I can change here, E and F here. Check. Here I can change these two. F and E, we can change it like this. Correct. And next case here I can change it as uh, D and C. D and C here. Correct. So again I'll get one more case here. This is one more case. Clear? E and C, F and D. F and D, A, B. Right. Only one change I meant to say. This one, this part of change will not come. So only one change you are getting here. And right. Now this is the way you have clubbed it, correct? Now change the clubbing part. That is, now you club it as AB, BD, AB, BD, sorry, AC, BD, and EF. If you club this and write it one more time, you'll get the rest of the five forms. And third time, you can make it as AD, BC, sorry, BE, and CF. Got it? So every time you change this way, you have to change the pairing part here. Now, let me show that. M, AB, CD, EF. This is one pairing you do. Next, AC, BD, EF. This is another pairing you do. Sorry, BE. BE and DF. This is the other pairing you do. And next, M, AD, BC, BC, AD, BC, and DF. Now, A, B, C, D, E, F again, right? So, B, C, E we did, C, E we didn't do. A, D, C, E, and BF. Done. That's it. Got it? Guys, this is the way to do it. So, you pair in these three forms and then write the same scenario one more time here. One I have done it as A, B, C, D, E, F. You'll get this 5. Then do the same thing with this one. A, C, B, E, D, F. Again, you'll get 3 times. And A, D, C, E, B, F. Again, you'll get 3 times. That is what it explains this part also. That is, you have to make it into 3 pairs. Those 3 pairs can be arranged in 3 different ways here. Correct? At 5 different locations. And of course, but AB and BA is one and the same. So now that is a formula you will get 5 into 3 factorial by 2. Got it? Clear? So I hope you understood, guys, what to do. Right. Next. The other case you can see here is if you have M, okay, if you have M, A2, BC, DE, M, A2, BC, DE. Got it? So now your A and A is fixed here. So that is, we have either you will have A and A in the transform in any one case, or you can have A and A in the cis case. That's it. A and A will be cis case. Only these two cases are possible. Rest all you have to rearrange. Correct? So while rearranging here, you will get 3 factorial by 2. These are the number of rearrangement of those 4 square planes. Correct? And plus here we have 4 different situations, because here on a plane, whenever there is a plane of symmetry, then you can have only these many arrangement, 3 factorial by 2. Okay. But if you have 2 different unique places, right? There are 4 ligands and 2 different unique places. Like this two, I mean, these 2 places are same, but these 2 places are different, isn't it? In that case, it will become 4C2, 4 positions and C2. So how many we can have here now? So total will be 3 factorial by 2 plus 4C2. So that makes it 9. Okay. So you can see there are 9 geometrical isomers in this case. Okay. Now listen up. When I write this case here, there are no plane of symmetry in any one of the case. So that means here I will get, you know, uh, here I will get 5 geometrical, 5 geometrical and 5 geometrical. And all of them are optically active. So optically active isomers, optically active isomers are 15, and stereoisomers, total stereoisomers are 30. Correct. Sorry, optical isomers are 30 and optical geometrical isomers are 15. So number of geometrical isomers are 15. Because every geometrical isomer which you are writing, they are all optically active only. So 15 are optically active, so 15 into 2. So total 30. All 30 are the stereoisomers. Okay. Got it? So I hope you understood MA2BCD, how to do this. MA2BCD. Okay. Next. In case if you have MAA thrice, then how do we need to look into it? Got it? So check. In case of MAA thrice, you will have M. We have 4 positions here. So we have A, and all positions here like this. Got it? So you know that they can only have the cis form. This is one cis form. The trans does not exist. So how many geometrical isomers? No geometrical isomers here. No optical isomers observed. There is only one compound. So there is no geometrical or optical observed. Got it? Sorry. Optical is observed because there is no plane of symmetry. You see neither this nor this nor this. There is no plane of symmetry ever. Correct? Kids get confused that, sir, why don't we write a plane here, and can you see that this one and this one are on the opposite side? So isn't it not the optical isomers? Actually, no. Okay, let me show you with a simple understanding here. Correct? How do we need to think? Suppose, imagine on this phone here, everybody, these 4 are the square planes. 1, 2, 3, 4. These 4 are the square planes. One above and one below. This is how the octahedral will be. Right. Now, if you notice, one AA is this way. This is AA. Okay, this is the way AA. And one AA is like this way. Okay, this is how from the center up, like this, correct? The next A is actually below here, this side, below here. So now the one which is below here and above here, they are not on the same plane to show it like mirror images. They are not like exactly mirror images to each other. So therefore, these would only show optical isomers. So there are how many optical isomers? Two. This and the mirror image. Okay. Next, MAA twice B2. In MAA twice B2, how does that structure would be? In this case, you would notice that MAA and B here. This is one scenario, correct? Or we can have these two also here, right? This is B and B here, A and A here. Okay. So this will be cis and this will be transform. So one is cis, the other one is transform. Okay. So one is the cis form, the other one is the transform here. Everybody clear? Now notice, in this case, there is a plane of symmetry. This entire thing is on one plane, and that is giving out these two cases. So geometrical isomers are two. Optical isomers are also two. So number of stereo isomers are three. Okay, because this one will not have any plane of symmetry. So let me write on that. Plane of symmetry is not present. Hence, they are optically active. Next scenario. Next scenario. This is exactly the same scenario as that of the above one. Same scenario. Instead of BB, now we have BC. That's the only difference. BB and BC here, correct? But notice here there is a plane of symmetry passing through this one here, this way. Since there is a plane of symmetry here, the logic remains the same. So there are two geometrical, two optical, stereoisomers are three. Please check. Any doubt? Right. What if you have MAB thrice? In that case, how many optical isomers we will have? How many geometrical isomers we will have? Let's see this case. Suppose MAB thrice is a very similar case as that of what we have earlier here, like this. See, check it out. So MAB thrice, I'll just write down these three structures first and then I'll change that part of it. So AB, AB, AB. So we have B here, and B here. And then we have, correct, like this. Now, what I can have, AB here, correct. So now A here and A here, B here, no, A, AB here, like this, B here, B here, and next one is AA here and BB here, right? BB here, B here, B here, and AB here, like this. This way. Now, how do we need to differentiate everybody? Please check it out. Here we have AB, which is connected with B and B here, correct? So both sides we have B and B, correct? So on this plane, please check out this plane only. On this plane we have AB, on the other side we have B and B. On this plane we have AB and then we have A and A. On this plane we have AB, right, and AB. Correct. We have AB and AB here. Correct. Now other form what I can write here. Other form what we can write here is that we have same thing like AB, correct? But now A and B are here and A and B are here, correct? That makes it B here this way. Okay, please check this out. Now what do we have? AB, AB here. So we'll have this as AB and AB. Okay, so which of them is same? Let me check it out once. Okay, so here we have A, A, A. Can you see this is like a meridional form? This is meridional form. And this is also meridional form, correct? So the same thing we are noticing here. We have AB and BB here like this. So AB and BB here like this. So these two are one and the same. These two are one and the same. Next, if you notice, we have AB and AA here, correct? So here also AB and BB here with AB and BB here with again A and A here. So do I get any difference? Mhm. Getting the same thing. AB, BB, AB. Sorry, these two are same. So here also we have AB, uh, so AB, BB, AB, BB, BB and BB here, and we have A and A. So AB and BB and A and A, AB and BB and A and A, AB and BB, A and A, AB and BB, A and A, AB and BB, A and A. Sorry, all of them have written it same only. So these are, you can see these are AB. This is different. Here we have AB and AB. No, AB and BB and A and A. Here, like this we have and AB and BB. Then we have A and AB and BB, and we have A and A. Here we have AB and BB and A and A. So structurally, all of them looks exactly same. There is meridional form. All these four are one and the same. Let me delete these cases because all of them are looking exactly same. Let me copy this once again. I'll put the one more scenario where you have. Okay. I think I need to change these cases one second. Let me rewrite that. So how I need to think is like this. This is a meridional form. So when you write any meridional form, again, you'll get the same scenario. Now I need to write the uh, facial form. Facial form is A here, and A here. Then we can have B here, B here, and B here. Right. Now it is different because now this is facial isomer. This is a face of the octahedron. Hence, this will be. Now, here there is no plane of symmetry. Here there is no plane of symmetry. So, plane of symmetry is not at all observed in all these both cases. So geometrical isomers are 2, optical isomers are 4, total stereoisomers are 4. And everybody, this is the form. Please check, everyone. Clear? Right. And the last thing is MAB twice B2. MAB twice B2 is like you have MAB twice and B2. You just make B and B trans to each other. Then we have AB here and AB here. So you can put it like this. This is one way. And the other one is just make sure they are trans to each other here also. So it is like B and A here. And the last one is you put them into the cis form now. B and B, you can put it as cis form. B and B in a cis form. So A and B here like this. And another form in this case, like what I can write here is B and A here. So we can have this as B and A here. So 4 different geometrical isomers we can have. Clear? Clear? Right. So M, A2, B2, C2 will have how many geometrical isomers are 4. So there are 4 geometrical isomers. Now notice this one. This has a plane of symmetry. This has a plane of symmetry. So just discard these two. Now here there is no plane of symmetry. So that makes it 2 isomers. Here there is no plane of symmetry, 2 isomers. So total, so 4 and optically active or 4 stereoisomers are 6. Done. Everybody clear? MAB thrice. These are the cases you need to know. Done. MA2BCD, I have already explained you how they look like. MA2B2CD also have explained you how does they look like. Correct? Now putting all of them together, how many stereoisomers you will have? I'll just write down these numbers. Learn that. If you have 3 different cases here, AA, BC, and DE, it is like A2, BC, DE. In such case, stereoisomers will be 10. We have learned that. Now, if these are bidentates, correct? AB is a bidentate and CD are monodentates. Then you will have 11. Then AB is a bidentate, CD is a bidentate, and EF is a bidentate. Okay. Then we'll have 20. Then you will have 20 stereoisomers. MA3, we just learned this has 4 geometrical isomers. MA2B2C will still have 3 geometrical isomers. This you can practice, everybody. Okay. If you write this down, you'll be able to learn it. Okay. Here I can write this scenario once again. Number of geometrical isomers in this case would be 6. Optical isomers will be 4. Stereoisomers are 8. Okay. So I worked out all the possible cases here, everybody. So if you go through it, these are all the cases you have to learn it. Got it? In which case, how many isomers we will have. Okay. Here also I'll fill this table for you. Please check. This is 15. We learned it. We learned this as 9. Then we get 6. This has 5. Then we have 4. This has 3, 2, 2, 2, 0, 0. Okay. These are the stereoisomers. Next. Same thing if you put it in stereoisomers and geometrical isomers space here, it is 2 stereo, 2 stereo, sorry, 2 geometrical. Basically, stereo is because of geometry here. So I'm writing it as 2 and 2. Then again 2 stereo in total, 5 in total, 15 in total, 30 in total, 60 in total, 8 in total, 3 in total, 10 in total, 11, 24. And only enantiomeric pairs, how many we have? 0, 0. This one also has 0. Yeah. This one will have 1 pairs, 6 pairs. Okay. And 15 pairs. 15 twos are 30. So 1 pair, 2 pairs here, 0 pairs in this. 5 pairs here, 5 pairs here, 10 pairs here, and 2 pairs here. Yeah. And this one we just learned it 2 and 1. Okay. This again, once you see the answers, you can just practice along what will be the cases. And I think this is going to help you out in going through all the forms of isomerization everybody. Okay. Learn the tricks mainly, when it comes to these marked ones, especially the marked ones are the ones which are most repeated ones. So whatever I have marked it, please go through them more often. Right. So especially like these three cases, 1, 1, 2, and 3. These three cases. Got it? Right, guys. Okay. So there is very small part left. I think we can catch up in the next class, but it's very small part though. But I want to do it very thoroughly. Got it? So that we can cover up in the next.